So today we're finishing up the Laplace transform, and we're going on to a combination of differential equations and some more serious linear algebra. So what we'll do is basically use a trick to change higher order systems into a bunch of first order equations, and those will be solved using linear algebra. That actually will be pretty cool. But before we do that, let's go on with the Laplace transform. So remember that we have this thing called convolution. Two functions, right? You have f and g, two functions, and then you involve them, right? You take the integral of one guy against the other guy, right? The integral of one guy against the other guy. And you can think of this as sort of an averaging of one by the other. Okay, that's roughly what goes on, averaging of one by the other. And what we said is turns out to be really good is that the Laplace transform turns convolution into multiplication. Okay, so for if f and g are sufficiently good functions, and that will become clear. What that means, what we'll need them to be able to do will become clear. If further the Laplace transforms of f and g exist for s bigger than a, then the Laplace transform of the convolution turns into the product of the Laplace transforms. So this Laplace transform exists, and it turns out to be equal to that product. So this will we'll see that this actually is very, very useful. Laplace transform turns convolution into multiplication. Okay, so let's do it. The proof is basically just a calculation. Right? If we look at the Laplace transform of the convolution, well, that's the integral from 0 to infinity of the convolution. E minus dt. You guys don't. If I were you, I wouldn't copy this down. I will send this to you. It's all right there. Just look at it. Okay. Right. Here's the definition of the Laplace transform. Right. Here it is. Right. You take the integral of the function against the exponential function. Right. That by definition is the integral, right, of the convolution. The convolution is the integral from 0 to t of f t minus alpha g alpha d alpha, or e minus dt. Okay. So you have this double integral, right? Okay. And the thing that we're going to do is we're going to change the order of integration, right? So instead of integrating first d alpha and then dt, we're going to integrate dt and then d alpha, right? So do you guys remember how to do this sort of thing? One has to take a little bit of care. John, you're not sure. So you have to think like this. Like if this is my t and this is my alpha, then what region am I basically integrating over? Well, as t is going to go from 0 to infinity, and as t ranges, my alpha goes from 0 to t, right? So basically, I'm integrating over this sort of thing, right? For every fixed t, I integrate from 0 to t. Integrate from 0 to t. My alphas range from 0 to t. Right? For every fixed, I fix t's and let the alphas go from 0 to t. Okay. Okay. So if I'm going to do it in the opposite direction, right? If I'm going to change the order, I'm going to do the alphas on the outside and then the t's first, right? The t is on the inside, so that's t minus alpha, g alpha, no, right? I want the UVSP, right? So I'm going to put everything involving, just for now, I'll put everything inside. Okay, well, what's going to be my ranges of t's then, right? The t's are going to go from, I'm going to have fixed alphas, and then for each fixed alpha, the range of t is what? Right, I'm going to slice this, I'm going to take this domain and instead slice it horizontally. Right, so I'm going to have fixed alphas, right? Alpha is going to range from 0 to infinity now. Right? And does it usually make the calculus 2? No, 3? Should be able to do this. Right? The t's are going to go from what to what? From get a whole like that. From alpha to infinity, yes. Right? The t's are going to go from alpha to infinity, right? Right? Because this is the line t equals alpha. Right? This is the line t equals alpha. Originally we were going from 0 to t, right? Alphas went from 0 to t. Now we're going from alpha. The t is going from alpha to infinity, right? And you see the advantage of doing that, right? The advantage is that, well, you can pull this guy out, right? Right? That thing doesn't depend on t, and you can pull it out. So we can change the order of integration. This is actually a theorem called Fabini's theorem that you can change order. So if f and g, if your functions are good, if the function that you're integrating, if the integrand is good enough, and in your top 3 class, we probably never told you what was good enough, and I'm not going to tell you what's good enough now, but if you want to know, then just go look it up. Look up Fabini's theorem. You can change the integration as long as the thing you're integrating satisfies some condition. Okay, so we integrate this thing, we don't integrate this thing. We pull that thing out, f of t minus alpha e minus st dt alpha, right? And then to make this thing look more like we're going to do the change of variable on this thing. So let c be t minus alpha. Let's let c be t minus alpha. Right? You get the integral from 0 to infinity of g of alpha, right? C, as t ranges from alpha to infinity, right? C is going to range from 0 to infinity, right? We get f of c, right? E to the minus st, well, t is c plus alpha, and then dt is dc because alpha is a constant, right? Inside that integral, alpha is a constant. Right? dr. Everyone all right? now it's starting to look more like the Laplace transform, right? It looked like the Laplace transform, except we were integrating from alpha to infinity, which is trouble. We changed it slightly, right? So this thing here is, of course, e to the minus sc e to the minus s alpha, right? And then we're done. Right? You see that we end up with the product of two Laplace transforms. Right? We get an integral from 0 to infinity, g alpha. I'm going to pull this guy out since it has nothing to do with c, e to the minus s alpha. Integral from 0 to infinity, fc, e to the minus sc dc, right, the alpha. Right? And then you see that this entire thing is constant with respect to alpha, and so we pull it all out of the alpha integral. Right? So we get the Laplace transform of f times the Laplace transform of g, evaluated at the same points, right? So the Laplace transform of f at s, and the Laplace transform of g at s. Sure.
But it doesn't matter that I'm just looking at the original sort of theorem, and it doesn't matter that you have a different variable than you started with in one of the Laplace transforms. I mean, because you started with, didn't we start with an f of t? Or something?
That's the dummy variable, right? That's the dummy variable. I can change this thing to whatever I want, right? Bananas, as usual.
Okay. It doesn't matter.
It doesn't matter, right? That's the dummy variable. You're integrating as your dummy variable as your variable goes from over some range. You can call that whatever you want. You can use a Chinese character. I've seen this in the Chinese math journal. Sometimes they use Chinese characters as their variables. Use Greek rather than Chinese. Do you know what the Greek people say when they say, Americans say it's Greek to me? Like, what do Greek people say? They don't say it's Greek to me. They say it's Chinese to me. Any questions? No? Simple, right? It's just a calculation. Right? The only thing that happens is you change the order of integration. And then after that, it's just, I guess there's a change of variables, but that's no problem. So, right, cool. Right? The Laplace transform takes convolution, which did not seem all that obvious to you, right? Convolution, sort of an odd thing to consider, but now you see it's actually something very natural. Right? On the Laplace transform side, it corresponds to multiplication. Right? So, as usual, let me show you a sample problem of how this works in the initial value problems. In 4y double prime plus 4y prime plus 17y equals some function. And we're not even going to say what function it is. You'll see that in some sense we don't need to say what that function is. Suppose we have it equal to some function g. And our initial value conditions are, as usual, helpfully chosen so that when we take a Laplace transform, all the constants vanish. Okay. So when you take a Laplace transform, you get that you get 4s squared Laplace transform of y plus 4s Laplace transform of y plus 17 Laplace transforms of y equals the Laplace transform of g. constants, thankfully, all vanish. And so you end up with a Laplace transform of y being 1 over 4s squared plus 4s plus 17 times the Laplace transform of s, of g, excuse me. Okay. And that might have seemed bad before, particularly since we don't know what g is, right? But now now you see what happens, right? We know we have the Laplace transform of y is the product of these two things, right? So Laplace, this is hopefully the Laplace transform of some function times the Laplace transform of some other function, right? And so you know about y. Y is going to be the convolution of the inverse Laplace transform of this times against g, right? Whatever this is, right? Let's call this thing h, right? Where h is the inverse Laplace transform of 4s squared plus 4s plus 17. So we know what y is, right? Y is just going to be y is going to be the convolution of h against g. And so the only thing we need to do is figure out what the inverse Laplace transform of this guy is. And as usual, we use completing the square and translation and this sort of thing. Okay, so I don't know if we really need to do this. I'm just going to write it down. 4s squared plus 4s plus 17 turns into 1/4 over s plus a half squared plus 4. Okay, and then when you take the inverse Laplace transform of that, you end up with 1/8 e to the minus t over 2 sine t. That's something that I'm sure you are tired of doing at this point. Okay, so that's maybe not so interesting, but you see what happens, right? That in the end, what do we get? We get that our answer is that y is going to be the integral of 1/8 e to the minus t minus alpha over 2 sine 2 minus alpha g alpha d alpha. Yeah. And so you see what's sort of nice about this is that no matter what g you have, you just put in g there. Right? You don't need to redo this problem. You don't need to redo this problem if somebody gives you a different forcing function. The answer is just going to be the convolution of this thing against g. So this is the last and probably the best trick for the Laplace transform. Yes.
Will we ever have to simplify that or solve that in a real?
Well, you can't because you don't know what g is, right?
But if they gave us,
If you had a
will we
g,
normally be solving this with just like g of t, not a specific forcing function?
I think so. I think most of the problems are just for general g. But if you have, I don't think they're going to give you something that's too complicated here. Right? If they did want you to simplify it, I don't think it would be that. It wouldn't be like this. It would be something simple.
Also, just to clarify, the g alpha in there is
Yes.
the inverse Laplace transform of what we have.
Or the Laplace transform of g.
It is, okay.
Right. So we didn't really get anything g. G because it's Laplace transform, and we took its inverse Laplace transform.
Okay, so it ends up in the original.
Yeah, it's just g itself, right? Because, right, you know that well, you know that y is going to be the convolution of the inverse Laplace transform of this against the inverse Laplace transform of this.
Okay.
Right, and so we get that y is the convolution of the inverse Laplace transform of this against the inverse Laplace transform of this, but the inverse Laplace transform of the Laplace transform of g is just
Okay.
I can't talk. Why did I become a teacher? I can't say derivative. I can't say Laplace transform more than once. I can't say Laplace transform followed by inverse Laplace transform. Okay. Is everyone all right with that? Okay. Pretty simple, but a useful tool. In the grand scheme of things, the thing to remember is the fact that the Laplace transform takes convolution to multiplication. That's really the important one. If we get to, no, I shouldn't say that. When you get to, in the future, if you do something using the Fourier transform, then you'll see that the Laplace transform, which is very closely related to the Fourier transform, the Fourier transform has the same properties. That it'll take convolution, to product, and that will be useful again in solving differential equations. Okay, so like I said, the next section really depends on linear algebra, right? We're going to use linear algebra like there's no tomorrow. And so, sections 7.2 and 7.3 are entirely sort of reviews of linear algebra. Let me just sort of go through things, and if anybody wants to hear about them, then just indicate, just raise your hand or like wink or something like that. You don't want to be obvious that you want to hear about it. Close your eyes.
Cough 3 times.
Yeah, cough 3 times. That's too obvious. Anyway, however you want to indicate. So, okay, so sort of crash course in linear algebra or review for those of you who have had it before. Okay, so I'm going to assume that you guys know what a matrix is. What a matrix is? What is a matrix? And I always write matrix as MX. The standard notation, like A alpha I j, and where I ranges from 1 to m, and j ranges from 1 to n, right? This is the number of rows, this is the number of columns. This indicates the ijth entry, right? The entry would be in the ith column, ith row and jth column, right? So A23 is the entry in the second row, third column. Right? I'm going to assume that you know what it means for matrices to be equal to each other. That means just every entry is equal, right? What addition means, you just add the entries. What the zero matrix is, what we mean by minus A, just multiplying a matrix by a number, and you just multiply every entry by that number, right? I'm going to assume that you know how to multiply matrices, right? So matrix multiplication. Matrix multiplication, and of course you recall that it's not the case that these things equal, that it's commutative. So matrix multiplication is non-commutative. You may be lucky, and you may have two matrices that do commute. Right? That can happen, but in general, it's not true that the products commute. We have I, the multiplicative identity. Right? The matrix, the square matrix, with ones down the diagonal and zeros everywhere else, right? The thing that you multiply by and which does nothing when you multiply it by it. Having a multiplicative identity gives rise to the notion of inverse, right? Right, there may be, if A is square, right, if there exists an inverse, a function, sorry, a matrix, sorry, B, such that AB is the identity and BA is also the identity, then we call B A inverse, right? We call that thing the inverse matrix, right? Once you have the notion of identity, you have the notion of inverse. Right? And then there's this thing about computation of the inverse via Gauss-Jordan reduction. Computation of the inverse using Gauss-Jordan reduction, which is something that everybody does at the beginning of the elementary course. Shut your eyes for 1 second. Is there anybody, raise a finger if there's anything that you'd like to see? Okay, open it. Thank you. So everybody's okay. Okay. The notion of the determinant, right? You define the determinant. One way of defining the determinant, and I don't know if this is the way you guys define it, you define it by expansion with minors down the first row or something like this, where you say A11, negative 1 to the I plus summation A 1j, negative 1 to 1 plus j times the determinant of the minor matrix. The minor matrix obtained by crossing off the first row and the jth column, right? We do this sort of thing. Right? This would be the expansion. Expansion down the first. Expansion by minors down the first row. Right? That's one way of defining the determinant. The determinant, these theorems about the determinant is non-zero if and only if A is invertible. If and only if the matrix is invertible. If and only if the null space of A is the trigonal null space, that is to say, the only solution to AX equals 0 is X equals 0. Right, the null space. Okay. For those of you who don't remember this term null space, right? The null space is just everybody who gets killed by the matrix. Right? It's all vectors. Let's say A is an n by n matrix. The null space is all guys in Rn such that Ax is 0. So it's all vectors that A will kill. Okay. And it turns out that for a square matrix, the null space is 0 is 0 if and only if the matrix is invertible. So you can check invertibility with this thing. Right. Properties of the determinant. Properties of the determinant. First off, that you can expand by minors the determinant along any row or column. you do your expansion by minors down the second column, you get the same thing as down the first column, etc., etc. Second, as a consequence, right, if you multiply a row of A by some number C, then what happens to the determinant? The determinant becomes the determinant of the new matrix. The determinant of the new matrix is then C times the determinant of the old matrix. Right? So these are consequences of part one. If some consequences, if you multiply a row, then you multiply the determinant. If you switch two rows, then the determinant of the new matrix is going to be what? The negative of the old determinant. Right, if two rows are called, maybe that's enough. Okay. Okay. That's another property of the determinant. We have this thing called the adjoint matrix, which is the transpose of the cofactor matrix. Okay. So you take this one. I think we saw this before when we were doing the method of variation of parameters, right? We saw this thing called the adjoint matrix. Just to remind you, you have a matrix A. So recall, you have a matrix A, and then you define cofactors A sub ij as -1 to the I plus j times the determinant of the minor matrix you get by crossing off the ith row and j column. So this is the minor matrix of A obtained by crossing off A's ith row and j column. So you take the determinants of those minor matrices, you give them a sign plus or minus, right? And that thing is called the cofactor. That's the cofactor. You use it. One uses it in the calculation of the determinant. Right? The determinant is the sum of the entries, right, against the cofactors, right, as j ranges from 1 to n, or as I ranges from 1 to n. When you're calculating the determinant. Okay. So these things are called cofactors. And we define the adjoint of A as the matrix as the transpose of the matrix of cofactors. As the transpose of the matrix of cofactors. And so you take all the cofactors and you put them in the matrix, right? A11 to A1n, etc., and then you transpose the guy. Right? You flip it across the diagonal, and that thing is called the adjoint matrix. And it turns out, this is the fact that we used earlier, recall that if you take A and you multiply it against the adjoint matrix, you get the determinant times the identity matrix. So I just put this as a fact. That, or another way of saying this is that if you take the adjoint matrix and divide by the determinant,